AI progress this week is looking less like make the model bigger and more like teach it to preserve the right evidence. Open systems are compressing long video without losing temporal structure, filtering medical corpora so quality beats raw scale, and training vision encoders to retain the tiny strokes and layouts documents demands sometimes outperforming much larger systems from OpenAI and Google on targeted tests. The common thread is modality-specific design, and we'll examine what it means for efficient multimodal systems, data pipelines, and AI products. Let's explore the first paper, 2607.14935. Video Chat 3, developed by researchers at Nanjing University, Shanghai AI Laboratory, Nanyang Technological University, and Peking University, is a fully open 4B parameter video multimodal large language model designed to unify short video perception, long context reasoning, temporal grounding, and live streaming interaction. Its central architectural contribution is the inflated 3D vision transformer, or I3D ViT, which extends image-based self-attention into chunk-wise spatio-temporal attention and performs temporal pooling before visual tokens reach the language model. With 4-frame chunks and 2x2 spatial merging, it achieves 16 times spatio-temporal compression. Adaptive frame resolution adds a state-controlled streaming policy. Silence uses a 224 squared pixel quota. Standby raises the next window to 448 squared. And response resumes low-cost monitoring. The training pipeline produces roughly 3M multimodal instruction samples through Video Chat 3, Academic 2M, Video Chat 3, LV116K, and Video Chat 3, OL617K, using evidence-grounded annotation enhancement, long video segmentation, clue verification, and a balanced state transition loss. Video Chat 3 scores 61.7 on Motion Bench, 75.6 on Temp Compass, and 35.5 average F1 on OVO timing, outperforming similarly sized open models such as Qwen 3, VL, 4B, and Momo 2 4B, while remaining competitive with proprietary systems including OpenAI's GPT-5 and Google's Gemini. Efficiency improves sharply with longer inputs. On 2048 frames, total latency falls from 44, 449s for Qwen 3, VL to 20, 412s for Video Chat 3. The authors release weights, code, training recipes, data sets, and data construction pipelines, making the system unusually reproducible. Let's explore the second paper, MedPMC, a systematic framework for scaling high-fidelity medical multimodal data for foundation models. MedPMC, developed by a Yale-led team, including researchers affiliated with Microsoft Research, turns permissively licensed PubMed Central literature into continuously updatable multimodal training infrastructure. Its 5-stage pipeline uses PubMedBERT for caption-based screening, vision transformers for panel detection and medical image filtering, YOLOV 10 for panel separation, and a supervised intern VL 2 54B model for caption alignment. Processing 6. 1M PMC articles produced 11M medical image text pairs with 95.3% of sampled images judged medically relevant, compare with 19.7% in a prior PMC-derived resource. The resulting MedPMC CLIP, initialized from OpenCLIP ViTL, 14 and trained under the architecture-matched BMC CLIP setup, improved average zero-shot AUC by 7.1 percentage points across 26 benchmarks spanning 11 specialties, despite using fewer than half as many pairs. Replacing the vision encoder in LavaMed improved medical question answering by 1.9 points on MMMU and 16.9 points on OmniMed VQA. GPT-4 was used to generate synthetic curation annotations, while Microsoft Research contributed affiliated expertise. In a clinical transfer test using 10,524 Yale New Haven Health System dermatology images, MedPMC CLIP increased morphology to image retrieval recall at 5 by 11.7 percentage points. The central result is that high-fidelity filtering, panel decomposition, and image text alignment can outperform simply scaling noisy biomedical corpora. Let's explore the third paper, Monkey OCRV 2, a visual text foundation model for document AI. Researchers at Huazhong University of Science and Technology and Kingsoft Office present Monkey OCRV 2, a document-native visual text foundation model designed to preserve character strokes, glyph details, and layout information that natural image encoders such as CLIP, Dino, and SAM often discard. Its MonkeyDoc versus 2 pre-training corpus contains 113 M document images spanning 17 languages, combining expert-labeled real documents with synthetic multilingual pages and cropped elements. The central technique jointly optimizes autoregressive image-to-text generation with pixel-level reconstruction, using mean squared error and, in document understanding experiments, edge and distance-aware structural losses. As a transferable backbone, Monkey OCR v2 raises CRNN text recognition accuracy from 58.7% to 67.3%, improves formula, detection, tampering, and overlapping text segmentation results, and lets a 110 mirror unimer net T outperform the 325 mirror unimer net B. Frozen and paired with Qwen 306B, it's 07B. Parsing model reaches 83.3% on multilingual MDP bench, up from 80.5% for the 3B dots. Magra, using a roughly 0.1B vision encoder on OmniDoc bench, it outperforms much larger systems, including Qwen 3VL2 35B and OpenAI's GPT-5.2, although specialized parsers remain stronger there. Under identical training with Qwen 3.1.7B, Monkey OCR v2B averages 57.2 across 8 document understanding benchmarks, surpassing OpenVision B by 13.2 points and outperforming encoders behind models such as Google's Gemini 3 Pro and Anthropic's Claude in the paper's broader comparisons. The study argues that document-oriented visual pre-training can serve as an independent foundation for multilingual OCR, parsing, and document intelligence. That's a wrap on today's AI paper highlights. Thanks for watching.